Welcome! In this explainer, we're going to pull back the curtain on something pretty amazing, how a computer can look at a line of code and actually understand what it means. We're going to explore the simple, elegant rules that turn plain text into powerful instructions.
So let's just start with a simple question, right? We type all these characters onto a screen, and somehow that turns into the incredible software we use every single day. But how does that translation from our language to the machine's world actually happen?
I mean, take a line of code like this one. To you and me, it's a pretty straightforward instruction. But to a computer, it's really just a sequence of characters. Before it can do anything with it, it needs a way to figure out the grammar, the relationships, and the meaning that's hidden inside that text.
Okay, so we're going to break this whole process down into 5 main ideas. We'll start with the simple fact that code is a language, and like any language, well, it needs a translator.
All right, let's dive right into our first idea, this notion that code is a language. And, just like any language, it comes with a fundamental challenge of translation. At its very core, a compiler's job is to be a translator. But it's not just swapping words one for one. It has to grasp the entire grammatical structure to understand the intent behind the code. It's kind of like how we need to understand the relationship between words in a sentence to get what it really means. So how does a compiler even begin to map out this hidden structure? Well, it starts by creating a kind of blueprint.
Yeah, instead of just reading the code as one long, flat line of text, the compiler completely transforms it into a structure. With some hierarchy, this blueprint is what reveals how all the different parts of the code actually relate to each other.
And here it is. This is that blueprint. It's called a syntax tree. And you can see right away how it breaks the expression down. You've got the assignment up at the top, then below that, the addition, and all the way at the bottom, the individual numbers and variables. It's basically a visual map of the code's grammar.
But, just having a blueprint isn't quite enough. To make it truly useful, we need to add notes to it, little bits of information that actually give it meaning.
The source material calls these decorations or attributes, but honestly, just think of them as sticky notes that the compiler attaches to each part of the blueprint. A note might say something like, hey, the variable y is an integer, or the result of y plus 2 is this new integer value. This whole process of adding notes is where the code really starts to take on its actual meaning.
Now, one of the most basic ways this information moves around the blueprint is by flowing upwards. We call this a synthesized attribute. So for example, the nodes down at the bottom represent the variable y and the number 2. Let's just say y has a value of 4. Okay, so that information gets passed up to their parent node, which does the addition. It then synthesizes a new value, 6, to pass even further up the tree. You see? The information flows from the bottom up.
Okay, this brings us to a really crucial point. For this entire system to work smoothly, there has to be a simple, predictable order for how all this information flows. You can't just have notes being passed around randomly.
And this gets us to the core idea of our entire explainer, a beautifully simple rule known as an L-attributed definition. The L here just stands for left, and all it means is this. When you're trying to figure out the meaning of any part of the tree, you can only use information from 2 places, from its parent, so from above, or from its siblings over to the left, which have already been figured out. No looking to the right, no peeking into the future.
This is a brilliant way to think about it. It's exactly like following a recipe. You can't start mixing the wet and dry ingredients if you haven't even measured the flour yet, right? You do things in order, you rely on what you've already done. This simple, step-by-step, left-to-right flow is exactly what brings a calm, predictable order to the very complex job of understanding code. Okay, let's move into our last section and see how this one simple rule is what makes modern compilers not just possible, but practical and incredibly efficient.
This quote from the famous Dragon book on compilers really says it all. This isn't just some abstract theory, it's a fundamental practical technique. Compiler designers focus on this L-attributed approach for one simple reason. It just works so well in the real world.
The real power of this rule is its sheer efficiency. By processing everything in a strict left-to-right order, the compiler can read our code just once, building up the meaning as it goes along. It avoids that chaotic and slow process of having to jump back and forth, which makes the whole translation incredibly fast and reliable.
So the crucial takeaway here is that the compiler builds its understanding step by step, incrementally, a lot like how we do when we read. We use the context from the beginning of a sentence to help us understand the end.
And this elegant, simple left-to-right rule is what makes that whole process possible for a computer.
So, if you remember just one thing from all of this, let it be this: a simple rule about direction, about only using information from above or from the left, is what brings a calm, predictable order to the enormous complexity of computer languages.
And that's a pretty peaceful thought, isn't it? That beneath all the incredibly complex software that runs our world, there are principles of profound, elegant simplicity. A simple sense of order that lets us build almost anything we can imagine.